los terroristas.
Hello and welcome back to another lesson in Algebra 2. This is Mr. Bean and you're watching our website there on flipmath.com for Algebra 2 going crazy. Why is it going so crazy? Because it's excited. It's hyper because it's hyper for hyperbolas. That's what we're studying today, and it is the last one of our conic sections. So let's review what we've covered so far in this unit. We have talked about circles, we have talked about ellipses, we've done parabolas, and now lastly today we will do hyperbolas, and then we'll cover, that'll be all of the shapes of conic sections. A difference with a hyperbola is they do look a little similar to parabolas, but we're going to have a basically if we sliced a cone straight up and down, you would create a hyperbola, and it looks like this. They're very similar to parabolas, but actually their equations are going to be very much closer to ellipses than to parabolas, as you will see when we get to the equations part. So let's label some things on your graph. First thing is to label, actually, you know what, don't even label the center. Okay, that's too obvious. You can put a dot there, but let's not write the word center because it's going to get really crowded in there. So leave off the word center. Just put a dot in the middle. Then I want you to draw a little rectangle here. It doesn't really matter how far up you go because we're just try to make it look like mine. We're just trying to eye it here, so it's going to be difficult to know exactly where the rectangle should go. And then we're going to label one of the foci, a focus there, and a focus there. Probably should have said focus as opposed to foci, but foci is plurals, and there's two of them. So we've got two foci on a hyperbola. Now next we'll label the vertices. So you have the one vertex here, and then you'll have another vertex on the other side. So again, hyperbolas have two foci, two vertices. Then you've got this thing called the transverse axis. And if I'm going too fast for you, you might want to pause so you can get these things written down. Write small, by the way, so you can fit everything in here. The transverse axis is this thing that transverses from the left side to the right side. It transverses the vertices. Okay, so I remember it going from each vertex across the hyperbolas. That is the transverse axis, meaning it is transversing. See the word transverse? It is transversing the vertices. You got to remember that. That's important. And then across this rectangle, if you go up and down on the rectangle, in this case it's up and down, but if you go the other direction, it's called the conjugate axis. Notice also how I am labeling it A, and I'm labeling this one B. So each side of the transverse axis is A, and each side of the conjugate axis from the center is B. That distance from the middle point to the edge is B. Next, you're going to draw a line from the center out here to the foci, and we're going to label that C. Okay, so we've got A from the middle to a vertex, B from the middle to the other side of our rectangle, that we'll talk about the rectangle in a minute, and then you've got the center to a foci is C. Again, just pause it if you're not sticking with me, that's fine. All right, next we have these crazy diagonal lines. What in the world is this? What I want you to do is sketch a dashed line from the corner of this rectangle to the other corner of the rectangle. These lines are the asymptotes of the hyperbolas. Notice how this, if we just kept going further and further off, here and here, and then down here, it would get closer and closer to this line. So if we draw lines diagonally through this rectangle, that creates the asymptotes for the hyperbola. So you could even label these as asymptotes. But the big question is, what's the slope? Okay, so what I'm going to do is come over here, and we're going to write down the slope of this line. So what is the slope of that rectangle of that diagonal line right there? The slope from the center is rise, run. That's a B divided by A. Okay, again, it's the rise and the run. What about the slope of this line? The slope of that line is negative B over A. It's actually the same slope, it's just negative. It's opposite, so because it's B over A, but the line is dropping. We're not going to worry about getting the exact equations of these lines, but it's good to recognize what the slope is of the lines because that helps you with sketching your graph. So there's your crazy visual. I know that's a lot of stuff. The biggest thing I would say on this that's new to you is these words transverse axis and the words conjugate axis. That's mixed up in all of these things. And the reason those are so important are because in some of your word problems, you're going to be given these words transverse axis and conjugate axis, and you'll have to go from there figuring it out. Just remember that the transverse is your A, and it is from the center to a vertex. Here we go with the equations, the standard equations of a hyperbola. Notice a couple of things about this in compared to the ellipse. They look very close to ellipses. It has to equal 1 on the right side, just like the ellipses do. But the difference is two things. One, we have subtraction. We have subtraction for the hyperbolas. But we also have, notice both these equations, we have a squared going in front. Okay, in the ellipses, we'd have a is greater than b. That is not the case for hyperbolas. A is not greater than b for hyperbolas. A is always the front number here on bottom. Okay, so recognize that because it's subtraction, the order matters now. With ellipses, the order didn't matter because it was addition, but now it matters. And it is not a greater than b for hyperbolas. So what else is the difference then? Well, what you've got is that these are hyperbolas that open left and right. That is when you have the x being first. So x values move left and right. I like to think of it that way. If the x comes first, the thing's going to move both left and right. But if it opens up and down, something like this, a parabola that opens up, not parabola, excuse me, hyperbola that opens up and down, then the y values are up and down. Therefore, the y values go first. Here, with your center still being at hk, just like normal, h comma k, but recognize that the h always goes with, I'll put a little highlighter here, the h always goes with the x. Okay, notice that? So just be careful with that. It goes with the x. And then the last thing to really even confuse you more is this little Pythagorean relationship. It's not the same as ellipses. Remember, in ellipses, the equation is addition, but this relationship was subtraction. With hyperbolas, the equation is subtraction, but the relationship for the a squared, b squared, and c squared is addition. Okay, it's the opposite. I know that's confusing, but you're just going to have to kind of get that memorized and figured out how these things work with each other. Now let's talk about c for just a minute here. That c, if I go back and look at this equation, this value c from the center out here to the foci, that's c. Now mine is not drawn to scale, but this distance right here, that distance from the center to the diagonal is supposed to be the same as that distance. So they're both a value of c. Hopefully you understand what I'm talking about here. They're supposed to be the same. Okay, you don't have to write that on there. Well, you can if you want, but that's what c is. Now you don't need to write this one down. I just threw this one on here just so you could see it, that here's the vertices, and in this case, the transverse axis would be here. On our other example, the transverse axis was horizontal, but in this one, it's always got to go from vertex to vertex. Okay, so just be aware of that. Transverse is always vertex. It transverses the vertices. So let's go ahead and do our first example. You're going to be given some information, and we're trying to write the standard form equation of each hyperbola. One thing you always want to do to start off is just kind of set up your fractions. You know it's going to be some quantity squared thing, and it's going to be subtraction, and it's going to equal 1. So this is my answer already. I know that's going to be the answer. Now we just need to figure out where's the center. So I'm going to write down up here the center, colon, and then we'll figure out, we got to figure out what A is, and we need to figure out what B is. So where's the center point for this? The center is right there. That's at 0, 1, so 0, 1. Oh man, my pen's doing horrible for me. And then my A value, how do you get this? Well, that is from this right here. Now, how did I draw that rectangle? Here's my recommendation. In fact, let me get rid of that. Here's how you draw the rectangle. They're going to give you the asymptotes if you have a picture of this. And on mine, you can kind of see that it's already there. But if you can't tell that it's there, it's real simple. You start at the vertex, and you go over here to the asymptote. Start here, go over to the asymptote. And then same down here, start at the vertex, over to the asymptote, over to the vertex, over to the asymptote, and then you just connect. There's your rectangle. Okay, so it's really not that difficult. And then that can help you out with figuring out your A. So your A always goes from the center to the vertex. That's 1, 2, 3, 4. So that's 4. And then the B, this direction, is just a 2. So we can go back now and complete that the A is a 4, B is a 2. So that gives us A squared, remember, always comes first. So we put 16, and B squared comes second, and that's a 4. Square your A and B. And then our coordinate point is going to be, let's see, it opens up and down. So it's going to be the y comes first, the x comes second, So the 0 goes here. So really, this x minus 0, we could have just said x squared on top here if we wanted to simplify this down. And then the second one is y minus 1 is the fraction that goes in front. And there's our answer for number 1. So the graphs are pretty easy if they start off with a graph. You just have to write the equation. Number 2, now we don't have a graph. So what I'm going to go do is down here in the corner is I'm just going to draw a quick little graph of what's going on. The vertices are at 0, 10, so somewhere up here, and 0, negative 10. So that means that this thing again is opening up and down. In fact, this problem is going to be pretty similar to number 1. And so we are going to need to find the center point. So where's halfway between, oh, wait, endpoints of conjugate axis. Let's do that next. So I'm going to use my red, change here. From this, the center is going to be at 0, 0. Oh, that's pretty easy because it's the midpoint of the vertices. And then the endpoints here are 6, 0, 0, 10. So here's your rectangle box thing, jig. And, oh, that's horrible to scale. But I just want to at least have a quick little sketch so I know a little bit about what I'm trying to do here. So my answer is going to be, if my center is at 0, 0, center, 0, 0, that makes this pretty easy because I know it's just going to be x squared y squared equals 1. And since it's opening up and down, I know that the y comes first. The x comes second, so y squared minus x squared. And now all we need is the a and the b. And then we can fill in our a squared and b squared. So what is the a squared? The distance from the center to the top. We said that point was 0, 10, this one here. So that means the distance there is 10. So we can just put 100 for our a squared. See, a was a 10. And then what was the distance from the center to the edge here? It was a distance of 6. So if b is 6, then a 36 goes here. And box our answer. Okay, before we go on with our notes, I want to show you some quick little examples of hyperbolas. Here you've got what Mr. Kelly loves to call the cloud makers. If you're in Mr. Kelly's class right now, ask him. Show him a picture of this and just say, hey, Mr. Kelly, what's this thing called? I bet you he'll say cloud maker. And this is the center right here. Can you visualize it? We've got a center point, and then right here. Can you visualize this hyperbola? Isn't that cool? So you actually have an application problem that's going to be similar to this. And, oh, that was bad. But recognize that this is the center point. That this is not the top of your rectangle. You know how you'd be making like an imaginary rectangle on this? Just be aware that this might be where the rectangle might go like way up there. Okay, just because the structure stops right there doesn't mean that this is the top of it. Same with this. This doesn't mean that's the bottom of our rectangle. Here, let me show you another example. Welcome to my living room. I have here a nice lamp with a beautiful shade on it. And you probably have one just like this in your house, maybe somewhere around. And what you most likely didn't realize is that you often have a hyperbola right in your home. So watch this. When I turn this puppy on, look at that. A hyperbola right on your wall. And this is actually a real hyperbola. So when the light comes out of the top of that shade, it's a circle, so when it comes out, it goes across and has a hyperbolic shape right there on your wall. Now if you'll notice on the bottom, I don't know if you can see it, but the bottom here is the circle is larger on the bottom of the shade, so the hyperbola actually is going out on a wider frame. It's not exactly perfect symmetrical, but if the shade was a perfect cylinder, then you'd have a hyperbola on top and bottom that would be exactly symmetrical. So next time somebody at your house turns on a lamp like this, you can be really smart and say, whoa, look at that hyperbola. Number 3. This one you're going to pause this one and do it on your own, okay? So if you haven't already done it, go ahead and pause now, and I'm going to have the answer appear here in just a sec. And there's your answer to number 3, x minus 2 quantity squared over 16 minus y plus 4 quantity squared over 144 equals 1. Now, if you didn't get those right, let me show you how this works. The transverse axis is horizontal, so that means my transverse axis is right here. And so I drew a quick little parabola that showed that it was opening left and right. What that did for me is that told me that the x came first because it's opening left and right. Now, what about these values here? The a equals 4 and b equals 12. I got those because it says that it's 8 units wide, this rectangle. So when I draw the rectangle, it is 8 units wide, which means that half that distance is only 4. And then if it's 24 units tall, half the distance from the center would only be 12. So there's my A and my B. All right, let's do one more example, and we are done with our notes. Vertices are here. Conjugate axis is 10 units long. So if we're given the vertices, then we need to find the center. Let me switch colors. And the center is going to be the midpoint between the vertices. So let's do -1 and -17. Take the average of those for the midpoint. Add them up, you get -18. Divide by 2, you get -9. If I knew how to do this in my head, I'd be faster. And then the next one, -10 plus a -10, divide by 2. Of course, you just get the same thing. It's the average, -10. So there's our center point. Now, what is going on with that? If you're at -1, -10, -1 down here at -10, there's one vertex, and then you're at -17, -10 way out here. The reason I'm drawing this is so I can kind of get a visual representation. That will help me with my fractions equals 1 so that I know which one comes first on my quantity squared stuff. So quantity squared, and if it's opening left and right, that means the x comes first, the y comes second, and the center then is -9 and -10, so +9, +10, and now all we need to do is figure out the A and figure out the B. So what is the A and the B? Conjugate axis represents the B. Remember that? Transverse versus the vertices. Transverse vertices. So conjugate is dealing with the B. So that is going to be 5 because it's half of how long the axis is. And then the A, how do we get the A? Well, let's put the 25 here first. Okay, so I'm going to box my answer even though I'm not done yet. Oh, that was a bad box. Now, what's the A value? Well, in this example, you have to use the center point, -9 to -10, and see how far you are to a vertex. That is a distance of 8. And so that means that A is 8. So we put a 64 here. So in this example, we didn't have to use the C value, so be careful because on the practice, you're actually going to have one similar to the ellipses where you have a focus, a distance to a focus, and that gives you C. And so don't forget that you have to use the relationship of C squared equals A squared plus B squared in these examples. Okay, so don't forget that. This part is when you get the focus. Okay, that's it for our notes. So I'm going to end with some things. You don't have to watch this, but it is kind of interesting. I think it'd be cool if you want to sit there for a minute and just watch a couple minutes, and that is it deals with sonic boom. I've got a little video clip from a website called redorbit.com. It's kind of cool. They've got a great explanation of when airplanes break the speed of sound, and that this actually deals right here. This is a hyperbola. When the sound travels on the ground, the sound barrier, the big sonic boom, when it travels along the ground, it travels in the form of a hyperbola. So just watch that little explanation, and I might even throw in at the end there some clips of some airplanes breaking the sound barrier. This is Mr. Bean signing off. Rock that mastery check, and I'll see you back in the next lesson.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to answer the question, what is a sonic boom? A sonic boom is the noise produced by something moving through the air faster than the speed of sound. But how is a sonic boom produced? As an object moves through the air, it forces air molecules out of its way, creating waves. These waves move away from the object or propagate. If the object moves faster than these waves can propagate, the waves become more and more compressed. Eventually, they're unable to get out of the way of the moving object quickly enough and combine into one large shock wave that trails behind the object. Sonic booms come from the shock wave created by an object moving faster than its own sound waves. The shock wave forms a cone shape around the object, with the tip of the cone at the front and the base trailing behind. When you first see the object, it appears to be moving without making any noise. It's only when the base of the cone reaches your ears that you hear the boom. In order to create a sonic boom, an object must move faster than the speed of sound, about 700 miles per hour. Sometimes physicists call this speed Mach 1. Anything moving faster than Mach 1 is moving faster than the speed of sound. Any object that moves faster than Mach 1 makes a sonic boom. Although we usually associate airplanes and spacecraft with sonic booms, meteors and other objects entering the Earth's atmosphere from space make them too. A whip's crack is a mini sonic boom created when its tip moves faster than the speed of sound. Even nature makes sonic booms. Lightning makes air molecules move faster than the speed of sound and causes the sonic boom we call thunder.